Lesson 3, Transformations of Logarithms. So before we start the transformations lesson, we're just going to review why it's not possible to determine certain values of logarithms. So here I have an example of log 0. And the reason why you can't evaluate this is because if you think about what this means, you have a base of 10. And so what you're looking for is 10 to some exponent is going to give you 0. Okay, and you can see that there is no exponent such that 10 to that exponent will give you a result of 0. Same goes here. 10 to some exponent would have to equal -3. So you can see again that's not possible. And 10 to some exponent would have to equal -10, which is also not possible. Okay, so for that reason you can see that you cannot find the logarithm of 0 or any value less than 0 as well. Okay, second question says, how are the graphs of the following functions related? And so you have f of x equals 10 to exponent x, and g of x equals log base 10 of x. And if I rewrite this so that it's a little bit easier to sort of compare the two functions, you'll see how these two functions are actually related. So this is like y equals 10 to exponent x, and this is like y equals log base 10 of x. Okay, so here you can see it's an exponential function. Here you can see it's a logarithmic function. Now if I write this in exponential form, it'll make it a little bit easier to compare the two functions. And so this would be like 10 to the exponent y equals x, using what we know about logarithms so far. Okay, and so if you compare these two functions now, you can see that here y is isolated, whereas here x is isolated. And here x is the exponent, whereas here y is the exponent. And so the way these two are related is that they are inverses of each other. Okay, so if I switch the x and the y, so let's say I switch the x and the y here, I get x equals 10 to exponent y. Okay, so if I look at the inverse here, I get x equals 10 to exponent y, which is the exact same thing as that function there. Okay, so how are the two functions related? Well, this is an exponential function with a base of 10, and this is a logarithmic function with a base of 10. And so these two functions are inverses of each other. Okay, so the graphs of f of x and g of x must be reflections of each other along the line y equals x, since f of x and g of x are inverses of each other. Okay, so just a reminder of some of the information you know about exponential and logarithmic functions. So just a little recall here, the inverse of an exponential function is a logarithmic function. So for example, here if you have the exponential function y equals b to exponent x, you can see that the graph is increasing, so that means that the base must be greater than 1. And so the inverse function would be y equals log base b of x. Okay, and again the base is greater than 1, and you can see that when the base is greater than 1, the exponential function is increasing, which in turn makes the logarithmic function increase as well. Okay, so there's a line of symmetry along here, and you can see that those two functions are inverses of each other. Similarly, if you're looking at a exponential function with a base that's between 0 and 1, you can see that the function is decreasing. And you can see that there's also a point here at 0 and 1. And if you look at the logarithmic function, which is the inverse, you can see that this function is also decreasing. There's a line of symmetry along here. And you can also see that there is a point at 1 and 0. Okay, so here you had a point at 0 and 1. Here we have a point at 1 and 0. So the x and y are interchanged. Okay, and again, the base of the logarithmic function is between 0 and 1, so that's why it's decreasing. Okay, we're going to compare some of the properties of exponential and logarithmic functions. So if we're looking at the properties of an exponential function, we know that the domain is all real numbers. It goes infinitely to the left and right. The range is greater than 0 because there's an asymptote at y equal to 0. And you can see the horizontal asymptote is y equals 0 here. Vertical asymptote, there are none. X-intercepts, there are none because there's an asymptote there. And then the y-intercept is at 0 and 1. Okay? The properties of logarithmic functions are the inverse. So the domain is all real numbers such that x is greater than 0. So you can see that it doesn't go towards the left. The range is all real numbers, so it goes infinitely up and down. In terms of a horizontal asymptote, there are none. In terms of a vertical asymptote, it's at x equal to 0. In terms of an x-intercept, you have a point here at 1 and 0, and then you don't have any y-intercepts in this case. Okay, and so you can see that because these are inverses of each other, the domain and range, anything that depends on x, and anything that depends on y is interchanged between the exponential and the logarithmic function. Also on the side here, you can see that I wrote log of 0, log of -3, and log of -10. These are the questions that we saw earlier in the review, and you can see that the reason why these were not, we were not able to evaluate these is because a logarithmic function only exists for values of x that are greater than 0. And so equal to 0 or less than 0, those values do not exist for a logarithmic function. Okay, so a little recall of transformations. So you know the general form of a transformed function. So y equals af of kx minus d plus c. A, k, d, and c, all those transformations are exactly the same as what you're used to seeing them as. One little thing that you need to remember is that vertical transformations are outside the bracket, so that's a and c. And horizontal transformations are inside the bracket, so that's k and d. Okay? The order of transformations is important. You want to make sure you do any of the transformations that require you to multiply first, and then the ones that add or subtract afterwards. And this is going to be important, a little note that's at the bottom here. Horizontal shifts affect vertical asymptotes. Because we're graphing logarithmic functions, every time you shift the graph left or right, it'll affect where the vertical asymptote actually ends up. Okay, so the effects of each transformation are still going to be the same. So a, k, d, and c will affect the base graph in the exact same way that it's affected the base graph of any of our functions. So whether you're looking at any base function or if you're looking at a logarithmic function, the transformations get applied in the exact same way. So a and c are still your vertical transformations, k and d are still your horizontal transformations. Okay, so to graph a logarithmic function of the form y equals a log base b of kx minus d plus c, the first thing you need to do is determine what the base graph is going to look like. So you want to figure out what the base function is. And so the base function will be easy to identify based on what the little number is next to the logarithm. Okay. Then you want to figure out what the key points of the base graph are. Now, this is going to be a little bit more complicated. So let's say you have a function like y equals log base 3 of x. Okay, so I just picked a random example. And so what you're going to know in this case is a couple of y coordinates, and what you'll need to identify are what the corresponding x coordinates are going to be. So let's say I'm looking at the first one where I know that the y coordinate is 0. What this point actually represents is where my x-intercept is actually going to be, and then the other one is just going to be another point on the graph. So those are, you only really need 2 key points on the graph in order to sketch the logarithmic function. So to identify what the corresponding x value would be, I'm going to replace y with 0, and so I have 0 equals log base 3 of x. If I rewrite this in exponential form, that'll give me 3 to exponent 0 equals x, which means 1 is going to equal x. So there's my x coordinate for the very, very first point. X will always be equal to 1. So you will always have a point at the x-intercept, which is at 1 and 0. Just like in exponential functions, when you always had a key point along the y-axis, the y-intercept, which was at 0 and 1. So you can see that it's interchanged because a logarithmic function is the inverse of an exponential function. Okay, and again, much like what you did with exponential functions last year, in order to figure out the second coordinate, or the second point, the easiest y coordinate you would have is 1, and so you can solve for the corresponding x coordinate. And so if you have y equals log base 3 of x, and if I make this equal to 1, so if my y coordinate's 1, I can solve for this again by rewriting it in exponential form. So I get 3 to exponent 1 equals x, which means 3 is equal to x. So in this case, just because my base is 3, I have a point at 3 and 1. Okay, so it's relatively easy to figure out your key points. You just need to know what the base function is. Okay, once you figure out your key points, the next thing you want to think about is what your new vertical asymptote is going to be. And your vertical asymptote here, remember, it's dependent on any sort of horizontal shift that you might have. Once you know where your once you know where your vertical asymptote is, you can sketch that on the grid. And what that'll help you do is create a barrier for your graph. So your logarithmic function will either be to the right of the vertical asymptote or to the left of the vertical asymptote. Once you have your asymptote, then you can create mapping formulas and use the mapping formulas to help you find the new transformed points. And then using the transformed points, plot your points, and then graph the transformed function. Okay, so for the first example, we're going to go through several steps in order to answer this question. So for the following logarithmic function, g of x equals negative log of 2x plus 2 minus 5, the first thing we're going to do is describe the transformations that must be applied to the base function to obtain the graph of g of x. Then we're going to sketch the graph of g of x, state the equation of the vertical asymptote, state the domain and range, and then finally, if 102 is a point on the base graph, state the coordinates of the transform point on g of x. So I've started the question on another sheet of paper, and you can see here that the first thing I needed to do is, before I can state any transformations or try to graph the function, I needed to factor out the value of k, which in this case was 2. And so I get negative log base 10 of 2x plus 1 minus 5. If the base is not given, you can assume that it's a natural logarithm, which is a base of 10. So in terms of transformations, the first transformation I see here is a vertical reflection in the x-axis. Then I have a horizontal compression by a factor of a half, a horizontal shift to the left 1, and then a vertical shift down 5 units. Okay. So in order to graph this function, the first thing I need to identify is what the base function is going to be. And in this case, because the base was 10, I know my base graph is going to be y equals log base 10 of x. Okay, and so what that means is now I can figure out my key points. So for my key points, I know that my y coordinates are going to be 0 and 1, and so I need to figure out what my x coordinates are going to be. So what I did here is I took the logarithmic function and I wrote it in exponential form. So this means 10 to the exponent y is equal to x. And so I took my values of y and I plugged it in here. So 10 to the exponent 0 equals 1, which means my first x coordinate here is 1. And 10 to the exponent 1, based on this, 10 to the exponent 1 is equal to 10, which means my x coordinate for my second point is at 10. Okay, so I have one key point at 1 and 0 and another key point at 10 and 1. Okay, and so using my transformations, I can figure out my mapping formula. And so in this case, my mapping formula is going to be 1/2 x minus 1. And my y values are going to be negative y minus 5. And if I plug in my x coordinates here to figure out my corresponding transformed points, 1/2 times 1 is 1/2, minus 5 is negative 0.5, and 1/2 of 10 is 5, 5 minus 1 is 4. So there's my x coordinates for my new transformed graph. And then my y coordinates will be negative 0 minus 5, which is negative 5, and then negative 1 minus 5, which is negative 6. Okay, before I can graph any of these points, what I need to figure out is where my vertical asymptote is. So normally your vertical asymptote is at x equal to 0. Because the graph has been shifted to the left 1, the vertical asymptote has moved to x equals negative 1. Okay, and so now I can actually graph the asymptote and then where my key points are and then sketch a graph of the function. So I have an asymptote at x equal to negative 1. So I'll graph that first. Okay, don't forget to label the vertical asymptote. And then I have my key points at negative 0.5 and negative 5, which is here. And then at 4 and negative 6, which is about here. Okay, so using my two key points, I can sketch a graph of the function, and you can see that it's decreasing as you go this way, and it should be getting closer to the asymptote towards the left. Okay, so there's the logarithmic function g of x, all graphed. Okay, the reason why the graph is decreasing, and you should recognize that because the base of the logarithmic function is 10, it should actually be increasing. The reason why it's decreasing is because the function has actually been reflected. So normally this is what a base greater than 1 would look like, but because it's been reflected along the x-axis, the graph is actually coming down and to the right. Okay, so it's decreasing for that reason. Okay, in terms of the vertical asymptote, we already know what this is. This is x equals negative 1. In terms of the domain, you can see that the smallest value of x is going to be a value greater than negative 1. And all my x values are more than negative 1. Not equal to negative 1, but only greater than negative 1. So x is an element of all real numbers such that x is greater than negative 1 is a domain. Okay, in terms of the range, you can see that the graph goes infinitely upwards and infinitely downwards. So it's going to be all real numbers. And then finally, the last question said if 102 is a point on the base graph, where would it appear in the transformed function? Well, that depends on the transformation. So we can actually use our mapping formula, which is 1/2 x minus 1 and negative y minus 5 to help us figure out where this point will actually move to. So if I plug in my x coordinate here, 1/2 of 100 is 50. 50 minus 1 is 49. And then my y coordinate, which is 2, negative 2 minus 5 is negative 7. So that's where my new point would actually move. Okay, so that's how you would do example 1.